Welcome back. I hope you're having an amazing time so far. Our next speaker is Peter Henstock. He is a machine learning and AI lead at Pfizer. Please join me in welcoming Peter to our virtual stage.
Thank you. My daytime job is that I work at Pfizer, but in the evenings I teach at the Harvard Extension School. And so this project is actually a representation of both those groups, where we have Tom Marmon from Pfizer and myself work with a group of students to produce this project. This is actually many co-authors on this project, as you can see. They did all the work, but the title is How Drug Labels Can Be Used to Understand Drug Patents. Since I work at Pfizer, this is my legal disclaimer for that. That the opinions expressed are only mine and not Pfizer's. So the idea is that drugs cost a lot of money to develop, 2.8 billion they say, and so it's important to protect the rights to those drugs, and the patent strategy is critical for that process. And so how do we actually understand what a company's patent strategy is? And more importantly, how can we understand which patents are really relevant to the drug itself, the important parts for the patient and so on? And so this is what this project is tackling. In order to look at this, we also use a combination of drug labels. And so we can see for a given drug, we can find a number of different patents that exist, maybe 1 through 23 different patents that govern the manufacturing, the design, the chemistry, and other aspects. We also have different drug labels, which can be found in the FDA. We have a first label, but then there's changes to this label that occur over time. The idea of this project is that we can track the changes in the drug labels and use that to figure out which patents are impacted those drug label changes. And so be able to track the source of a particular change back to a patent is the goal, because it tells us which patents are important for that particular drug that would affect the label change. Manufacturing changes would not, but important aspects of the drug would be a result of a change of the patent. And so how can we actually go and find these different things out? Well, it requires bringing a lot of different sources of information together. We focused on small molecules, and all of these are listed in the Orange Book. It is an Orange Book, and it has the patent numbers and all the drug names associated with it. Using the patents, we can go look it up in the USPTO, the source of all the different patents. But with the name, we can go look up the FDA site, labels.fda.gov, and find not only the current labels, but all the historic labels for drugs. And so it's the three sources that are coming together to make this project possible. But how does it really work? Let's go into one level of detail more. So we start off with an Orange Book, as I mentioned, and every drug is listed there that has a small molecule associated with it. And so we have a drug name, but it also has, very importantly, the list of patents that are associated with that drug. Without that list, it'd be very difficult to execute this project. And so we go through each of the patents, download it, and identify all the different claims associated with that patent. Similarly, we go to the FDA drug labels and take not only the label, the current one, but all the labels, the historic ones as well. And we identify the changes of the label that occur over time. And so we're looking at these deltas, these change of drug labels against the patent claims, and doing a matching using natural language processing to figure out which label changes are associated with which patent claims. And then the results are then displayed in a browser. One more detail is that there isn't just one Orange Book that actually is a historical set of these things, because it only covers the current list of patented drugs, and things that go off patent or things that were released earlier may not be in there. And so we use the Wayback Machine to extract older copies of the Orange Book. So the solution for this is that we're really trying to figure out, and first of all, visualize how drug labels change as a function of time. So this is actually an interesting thing by itself. You can look for a given drug and then see how the different label changes in the different sections. The second piece is take each of those separate changes and identify how the patent claims are associated with that. This is one of the things that we're delivering. And the third part is be able to do a matching against all those patents, against all those drug changes, and then export the full set for use in other systems. So I won't go a live demo, but instead just show you some screenshots, given the interest of time, of what the program looks like. It has been built, it is available in open source. but we're looking for a drug and we type in epinephrine. It gives us a list of all the different drugs. It gives us the FDA numbers, the NDA numbers, and so on, and allows us a chance to go and dive into the labels. We can get extra information on the drug and the labels from there. But once we go in there, we can see the changes that have occurred over time to a particular drug label. And it's done basically using diffs. We take one label, look at the next label, and very much like we use for source code, you can see what's changed, what's been added in green, and what's been removed shown in red. And so we're looking at the additions and deletions, and we can do that between any two different time points, from maybe the first label to the last label, or any combination in between. So we've identified the things that are changing over time within the drug label. The question then is, how does this affect the patents? Or how is this affected by the patents, rather? Which patent claims are most similar to this data? And so we then click on one of these labels, we end up with the right screen, which shows, oh yes, this particular patent, particular claim number 2, has a score with a 66% match. And so this is a pretty good match to a particular claim on the left side. And so we can get a left-right view of a change of a patent label, change of a drug label, rather, to a change of a patent label. And we can do this for all the different changes of the drug label and all the different patent claims associated with this particular drug, epinephrine. We can actually go through and highlight different regions and see which way regions go back and forth. We can also dive into different time points and say, well, we'd like to know exactly when this particular wording came into play. We have different colors of this lollipop view down below, which is a timeline. And so the first changes will occur in to that were shown in green, the next ones are shown in blue, and eventually the last changes are shown in red. And so we're identifying the different changes that have been enacted over time and fully getting the patent changes associated with any of these particular ones by changing in it. And so it's a very nice UI that allows a user to fully understand all the changes and all the patent claims to that. Again, the results can be exported so that you can look at all these things as a table in Excel format. So how do we actually build this? Well, it's actually a fairly complicated workflow, but we'll walk through the different steps. The first step, of course, is data retrieval. I mentioned 3 different sources. There's the Orange Book, there's the FDA Daily Med, which has the drug labels, and the Patent Office, USPTO, which has all that data. Whenever the Orange Book changes, we need to trigger changes to all these different groups to keep the information up to date. The next step is processing all these downloaded files. We need to extract and store all the text so we can view it. But we also want to identify the label changes that have occurred over time, and then apply some machine learning, natural language processing algorithms to compare the changes of a drug label to a patent claim. And the last step, of course, is viewing it all together with the user interface, allowing the user to query which particular drug they are interested in, and also visualize the results. Let me go one level deeper on this. All right, so there's a cron job that's looking over time periodically to say, has the Orange Book been updated? It's updated a few times a year. And so whenever there's a change of the Orange Book, that means there's been changes to the drugs, changes to the patent claims, and there will have new sets of labels, new sets of patents. Everything has to be downloaded again. So we update all the database with all these different new pieces of information that have changed. And for the NDAs, the new drug applications in the Orange Book, we have to mine those and extract the different pieces of information that are new. We also go through the patents, which are also associated with that, and extract all those details. Finally, we have to go match the labels changes and the patents, update the scores that are stored permanently, and so we can allow these to be viewed or exported by the user into a CSV format. So a little more detail on the data sources. There's weekly updates to the USPTO, and we have different claims digests. We've extracted the patents from 1976 to 2014 relevant to those particular drugs that are in the Orange Book. We use not only the current version of the Orange Book, but we use the Wayback Machine, the Internet Archive, that allows us to go look at the Internet in past times and extract previous information. And so we're getting the indices of the new drug applications, the NDAs, as well as all the patent numbers to make this connection here. going back, we're parsed the orange books, not only the current ones, but we actually go back to 1985. There's different formats for different versions of these, but we're using the NBER research data set for these things. For the drug labels, we use the Daily Med. It allows a nice, easy download for all the drug labels periodically, as well as different updates periodically. And so OpenFDA and Daily Med are the great sources for those two pieces of information. So the main challenge we have is to try to figure out the changes of the drug labels and identify how that maps into the patents. But how do we actually perform that matching? And specifically what we're trying to do is we have this section that's just been added to a drug label. And it's a fairly complicated section about different doses of morphine and so on. How does that relate to any particular patent claim that describes as this, which talks about pHs and other things? Is this a match or is this something different? So this is the natural language processing portion, which is quite a difficult problem, as you can imagine. And so what we do is we convert each of these sets of text into some large vector. If we have two different vectors, well, we can use a cosine difference to say whether or not it's a low angle, meaning it's very similar, or a larger angle, suggesting it's quite different. But how do we make this, how do we map this text into a vector? There's actually a number of different techniques that have come out in the last few years to do that, all using natural language processing. And the most famous of these is the Burp Models. And so these came out from Google and have different training sets associated with them. The opportunity is to identify the sentences, break them up into words and adjust it, or we could just run it all into an algorithm and then have it produce a vector. And so we did an assessment of all these different approaches to see which ones would work the best and produce the most meaningful vectors. But even that part wasn't trivial. The way we did it is we didn't have a training set and a test set because it's very difficult to create a large enough set for training. And so what we did is we took a set of random drug labels and some unrelated patents and said, well, how well do these match? These produce some kind of a distribution. And then we took a different set of data where we know that the patents relate. And so we saw the green ones are related, the other ones are unrelated. And as you can see, there's quite a difference in these two. And so the shift between the green and the blue indicates that which algorithm would work best. And as you can see, the ones that furthest shift to the right in the green will be the best result. The result came from actually the MPNet base, and so we selected this one as our best overall result. And so the successful outcomes of this project is that we were able to deliver a way to understand the drug changes in drug labels against the patent claims. We did this historically using a novel visual interface. It also shows the matches between different drug labels against patent claims, and all these results can be exported. And finally, we provide insight into the patent strategies for different companies. Thank you very much. All the source code is available. It is open source, and there's also a website available for this database and UI. Thank you very much.
Peter, that was amazing. Thank you so much for sharing with us. If you can stop sharing your screen, I know this virtual audience wants to give you a huge virtual round of applause. Thank you again for your time today. And for the audience, it's time for you to make your way to your next session. Along the way, make sure you accept your connection request and take some time to check out our awesome exhibits. Thanks so much, and we'll see you around.